Before we move on to a new topic, let's recall what we actually have learned from the earlier part of the module about abstract classes. To solve the polygon problem, we know that it is not really possible to really define the get area method in the polygon class, which is the common parent class for the rectangle and also triangle classes. So that's why we have to make at least one method that's in the common parent class polygon as abstract, namely the get area method. And right now, we're actually going to think about, is it possible that maybe in a single parent class, maybe there's nothing we can really define at that point. Maybe in the parent class, all the methods should be abstract, meaning that none of the methods can be really defined with a very specific implementation. So that's something we would like to see. And that's really the essence for interfaces. But as usual, let's now study some motivating problem that's simple enough, but also detailed enough, so we can see every aspect for the construct, in this case interfaces. And then I'm gonna compare and contrast about, in general, when should you choose to use abstract classes and when should you choose to actually use interfaces. So that'll be the roadmap for the remaining part for this particular module. Okay, so let's now take a look at the interfaces. Some motivating problem. Let's say we want to implement the two-dimensional points. We did learn about the point example when we in the very beginning of the semester, when we learned about how to implement the point class, with x and y. However, there's only one possible solution. So now we want to talk about, what if we actually got two possible alternative solutions? Both are valid, but somehow we want to interchange them from one to another without affecting the colors. So that will be the goal. Let's see. So there are two possible ways to really represent the two-dimensional points. So there are two. I'm pretty sure one of them which is about Cartesian. What about the other one? Let's take a look. So this, let's not worry too much about the detail for this diagram. I'm going to illustrate that visually in a moment. But let's now go over some principle. So the first system is called the Cartesian system, where we simply store the absolute positions of x and y. So this is normally the system you're very used to. The other one, maybe you did it in your linear algebra class, maybe, or maybe in your calculus class. I'm not too sure. Either way. Okay, so there's another one called so-called the polar system, in which case you're going to store the relative position rather than absolute. But how do you what do you store? You have to somehow store the angle in the units of radian. Okay, that's something I will also give you some information, right? But it's not really a math lecture, but at least the basics, you can definitely use that as a background. And also we have an angle, and we simply call it phi, and also the distance from the points to the origin. The origin will just be 0, 0. Okay, so that's kind of the two systems that both will work, both are valid, and we really want to say dynamically we can switch from one to another, right? That's something we want to make it happen. So let me now visually illustrate something quickly for you, just about the polar system. Also compare and contrast that with the Cartesian system, so you understand how the two alternative solution will work for the same problem. Okay. All right. The first illustration I'd like to do. So we talk about Cartesian over here versus polar over here. Okay. For the Cartesian, it's very straightforward. We're just storing the absolute position for the points, right? So this is the absolute position. Well, simply just be x and also y. So you can think about these will be the two attributes that we're going to declare in the Cartesian point class, for example, right? What about the polar system? In the polar system, we also store two attributes, but we're going to store in an implicit way, like indirect way. So we store the distance over here. You can see this r over here is the distance between the points and, let me just make it a little bit thicker, between the origin and also the point itself, right? You can see that's the r. And we store another value over here, which is a phi over here, right? Either you can spell it out phi, or you can simply just write like that, okay? Either way, okay? So the phi is really the angle that's between, angle that's actually over here, right? That's the angle over here. So these are the only two attributes we will store for the polar system. And now you want to know, why are these two systems equivalent to each other? It's simply because given this, I will be able to convert into this. And also given this, I will also be able to convert into this. So that's kind of the idea, right? So now, how do we do that? Well, let's talk about this one first. Let's say I actually got this system over here, the polar system, and I actually got a distance between the point and the origin. I also got this angle over here. And now, how do I actually calculate the corresponding x and y, which will be x over here and also y over here, right? How do I do that? Well, we have to use a little bit math over here, okay? Which is nothing complicated, but that's something you learned earlier. You just need some brush up. Okay, so let's now see how we can convert from polar into Cartesian very quickly. So this part over here, you can see this part is x, right? And this part over here is y. But how do we actually calculate them based on r and phi? Well, you definitely need some trigonometry, right? Let me just review that quickly with you. So you can see this part is really x, and this part here is really y, right? But how do we calculate x? Well, you can definitely see that it's going to be r times the cosine of 5, right? That's how you calculate the x. All right, that's well, you can definitely review what the definition is for cosine and sine. Okay, so this will simply be r multiplied by cosine of phi. Okay, well, that's exactly what I said over here. Well, this is more like a closer to the programming syntax you have to write later in Java, but we'll see. Okay, and what about y? Well, it'll be very symmetric. In order to calculate this distance over here relative to this and also this, it's going to be this multiplied by the sine of 5. Okay, so that's going to be r multiplied by, mathematically, the sine of 5. Okay, so that's about these two conversions. And so that means eventually what we have is this. In order to calculate from, over here, in order to calculate from the polar into Cartesian, you can see the x value will just be r times cosine 5. So this is what we actually just talked about. And this part over here, y, is going to be r times sine 5. Okay, so that's about the two systems. Right, you can just review these two very quickly. You don't need to memorize anything here. Maybe you just need to remind yourself about the definition for cosine and also sine. That's the only thing. Okay, and notice that again, for these two systems, especially for polar, right? Let me just write one more thing to notice. Okay, so here, so these are kind of indirect relative position of the point as opposed to direct over here, right? That's the main point you actually want to understand. Okay, and then both solutions are valid. So now the question is, dynamically, we want to be able to convert from one to the other, right? Easily. Okay, so the goal really is at the programming goal is dynamically at the runtime, dynamically switch will convert between two systems seamlessly. So you can think about every time when you for the same problem, you actually got like a several or alternative solutions which are all valid or both valid. In that case, it's a very good hint that you may want to use interfaces. Okay, that's some background for the problem. Okay, let me now go back and let's now go over some slides over here. Right. So as far as users of a point object P is concerned, so here user are like a caller, right? Whenever a caller actually want to say, for example, P statically is defined as points, but point may be part of the inheritance hierarchy, in which case we got two subclasses. Maybe one subclass is Cartesian, the other subclass is actually polar. And now that as far as a caller is concerned, they will only say P.get_x and also P.get_y. In that case, what exactly will be the version of get_x and get_y, right? So now it could be that in one version, get_x and get_y will just return whatever that's actually stored in the Cartesian system, just attribute values. On the other hand, get_x and get_y may involve the computation in the polar system, which are going to calculate these two values based on the store attributes r and phi, right? So there are two different scenarios behind the scene at the runtime. As far as the caller is concerned, they cannot really know which one is actually being called unless maybe they do some instance of check on the P, right? But for us as a programmer, for the developer, for the points, we have to be careful. And of course, this one here should be p.getY. I'll fix that. All right. Okay, how p.getX and p.getY are internally computed either by just returning the attribute values x and y, or by some trigonometry computation over here, is up to what the dynamic type is for the context object P over here. Okay, it's a very important slides already for you to actually understand. Once you understand this, I think the rest will just be about setting up some example to really show the equivalence between the two systems and also give you some example code, and that's it. Right? The interfaces is not a very difficult idea. You can think about, as I said, it's a special case for abstract classes, but we'll get to the syntax in a moment. Okay. In the next slides, I just want to actually show to you the running example we want to go over. I will also make available the source code to you, so you can also take a look on the Eclipse and also try to step into and see the dynamic type. I'll show you that at the end of the module. Okay, so this is the layout for the example that I would like to actually show to you between the two systems. Let's now go over this example quickly. Okay, and for your information, right, I didn't make it up. So sine 30 degree will be 1.5. Okay, just half. Okay, 1/2. Cosine 30 degree will be half times 1/2 times square root of 3. All right, so these are the fixed values. I just want to remind you. All right, and the way we're gonna set up the triangle, because this is the point that we want to actually represent. So this is the point to represent. Okay, and remember we actually got two systems, right? Let me just show you the setup, and I'll do a little bit of reasoning together with you just to make sure you're okay, right? Let's say for Cartesian system, right? So we're gonna store we're gonna store a times square root of 3, and also a. So this is x, this is y, and so this is what we call the Cartesian system. Okay, just make sure I how this. Okay, just suddenly forgot about how to spell that. Cartesian system, in which case we only store these two values, only store this value over here for x and this value here for y. Okay, what about the polar system? The polar system is going to be like this. Okay, so we got the distance between the points and also the origin, and also we got the phi over here, 30 degree. Okay, so these are the two things we want to store. Okay, so 2a we want to store, and also 30 degree we also want to store. All right, so these are the two attributes we want to store in the polar system class later on. Okay, so this is the polar system. So why is this setup valid? Okay, so what we need to what we can calculate very quickly is, you can see this is 2a over here, and that's the phi, right? So what will be the value for example, x and y, right? Let's now do that little proof very quickly, just to, this might be also some inspiration for you to set up the test cases, later, right? So this will be y, right? Y, by definition, we know that y should be r times sine 5, right? That will be r times sine 5, okay? And we know r is actually 2a. Multiplied by sine 30 degree. Sine 30 degree is 1/2. 1/2, which will be just a. Right? So that's why you can see a over here. So that's the y value. And that's really corresponding to the y over here. So we just prove about the y, right? It's actually equivalence. Okay, let's do one more just for completeness, right? And this one over here is the x, right? By definition, the x value will just be, right, you can see it's r times cosine phi. R times cosine phi, which will be, so you can see the r is 2a. multiplied by, and cosine 30 degree, right? You can see it's 30 degree over here. It's 1 over 2 square root of 3, which will be, well, it will be a times square root of 3, right? You can see that's exactly what we have over here, right? And you can see that's matching the x over here, right? So now we actually got the same triangle over here, and the triangle that's actually underpinning the representation for this particular point over here, right? Either we got the polar system, either we got the Cartesian system here, only got x and y, or we got the polar system. Right? If you do the conversion from polar to a Cartesian, for example, you definitely got consistent result. So that's what I'm trying to say here. So this is a valid example. All right, and also, yeah, that's exactly what I said over here, right? You can see the polar versus the Cartesian. Okay, I'll leave that some extra study for you. Okay, so that'll be the setup for the example. All right, so now, given that we know about this example over here, oh, one more thing to say. The real value about this setup is, you can see I simply say 2a, for example, 2a. So what is a? A can be any integer or double, any numerical value. For example, I can set a to be, let me just give you one example. If I just set a to be, when a is equal to 3, for example, right? In that case, 2a will be 6. And also, this will be 3 multiplied by the square root of 3, right? And also, let's say here, this will be a times square root, over here. So this will be just a, which will be 3, right? And we know very well from some theorem, which you learned maybe in the high school, right? For the right-angled triangle over here. In that case, we know that the square of 3 plus the square of this plus the square of this. So this will be 3 times square root of 3 square. That should be equal to the square of 6, right? You can actually double check. All right, that's going to be the case. Okay, so you can definitely set a to be any numerical value, and then all the sides are just going to be scaled accordingly. If you just follow 2a and then a times square root of 3 and also a, as long as you follow that. Okay, let's now go back, and then let's now try to declare some interfaces by learning the syntax.